Download this code from codegive.com, link in the description below. Understanding and debugging bug, some bad value integer parameter out of range 4. In Linux kernel development. This error message, bug, some bad value integer parameter out of range 4, is a critical one encountered in Linux kernel development. It signifies a kernel panic, meaning the kernel has detected an unrecoverable error condition and is halting the system to prevent further damage. This is a serious issue that needs immediate attention and thorough debugging. This tutorial will delve deep into the anatomy of this error, its common causes, debugging strategies, and preventative measures. We'll use a code example to illustrate a specific scenario and walk through the debugging process. 1. Anatomy of the error message ****. The core of the error message is, bug, some bad value integer parameter out of range 4. Let's break it down. ***bug***. This prefix clearly indicates a kernel bug, a condition where the kernel's internal logic or data integrity has been compromised. ***some bad value***. This is a placeholder. The actual error message will replace this with the name of the integer parameter that is out of range. For instance, it might say bug, page_offset integer parameter out of range 4, or bug, array_index integer parameter out of range 4. The name of the bad parameter is your first clue. **integer parameter**. This explicitly states that the issue revolves around an integer value. Integer overflow, underflow, or misuse of an integer value as an array index are common culprits. *out of range 4, this specifies that the integer value is outside the acceptable bounds for its intended use. The will be replaced with a more descriptive context, often pointing to the function or operation where the error occurred. This context is extremely valuable for narrowing down the source of the bug. Complete example ***. 2. Common causes ***. This type of error commonly arises due to the following issues. Integer overflow / underflow. Calculations involving integers can exceed the maximum or fall below the minimum representable value for the integer type. This can lead to unexpected results, especially when used as array indices or sizes. Incorrect array indexing. Accessing an array element using an index that is negative or greater than or equal to the array's size. This is a classic memory safety violation. Type mismatch. Passing an integer value of the wrong type, example unsigned long instead of int, to a function that expects a value within a specific range. Incorrectly sanitized user input. If your kernel module or driver receives data from user space, failing to validate and sanitize that data appropriately can lead to out-of-range values being used in kernel operations. Off by one errors. Subtle errors in loop conditions or calculations that cause an index to be just outside the valid range. Data corruption. Memory corruption elsewhere in the system can sometimes overwrite an integer variable, causing it to hold an invalid value. Incorrect pointer arithmetic. Calculating memory addresses using integer arithmetic can lead to out-of-bounds access if not handled carefully. Bug in upstream kernel code. While less likely, the bug could originate from the kernel itself. If you suspect this, consult the kernel mailing lists and bug trackers. 3. Debugging strategies. The key to resolving this type of kernel panic lies in meticulous debugging. Here's a systematic approach. Analyze the call trace, stack trace. The call trace provided in the error message is invaluable. It shows the sequence of function calls that led to the panic. Start by examining the function at the top of the trace, the one that panicked, and work your way down. Pay close attention to the function names and their parameters. Look for functions you wrote or are familiar with. Asterisk identify the critical parameter. Asterisk the error message itself names the bad parameter. This is your primary suspect. You need to trace where this parameter comes from, how it's calculated, and what the expected range of values is. Asterisk code review. Asterisk carefully review the code surrounding the function where the error occurred. Look for potential integer overflows, incorrect array indexing, or type mismatches. Pay attention to loops, calculations, and function calls. Asterisk print statements. Print k. Judicious use of print k statements can help you track the values of the suspect parameter and related variables. Be mindful of potential locking issues when using print k in interrupt contexts. Use pr_info, pr_debug, pr_warn, and pr_error according to the severity of the potential issue. Asterisk assertions, bug_on, warn_on. The kernel provides macros like bug_on and warn_on that can be used to check for error conditions and trigger a panic or warning if a condition is not met. These are excellent for verifying assumptions about the values of variables. Asterisk kernel debugger, GDB. For more complex debugging scenarios, using a kernel debugger like GDB allows you to step through the code, inspect variables, and set breakpoints. This requires more setup and knowledge but can be extremely powerful. You can use kgdb or kdump to debug a running or crashed kernel. Asterisk memory sanitizers, Kazan, Kameson. These tools help detect memory safety violations, such as out-of-bounds access and use after free. They can be enabled through kernel configuration options and provide detailed reports when errors are detected. These can be invaluable in cases where memory corruption is suspected. Asterisk check for data races, locking issues. If the integer parameter is shared between multiple threads or processes, a data race could be corrupting its value. Ensure proper locking mechanisms are in place to protect the variable. Asterisk consider compiler optimizations. Asterisk sometimes, aggressive compiler optimizations can introduce bugs. Try compiling with O0, no optimization, to see if the error disappears. If it does, then the optimization might be the cause, and you'll need to investigate further. 4. Code example and debugging walkthrough. Asterisk. Let's consider a simple kernel module that contains a bug that can trigger the bug, some BadValue integer parameter out of range 4. Error. Explanation. Asterisk. This module allocates an integer array my_array of size array_size, 10. The buggy_ function attempts to access an element of this array using the provided index. The crucial problem is that buggy_ function doesn't perform any bounds checking on the index parameter. In my_module_init, we intentionally call buggy_ function, array_size, which attempts to access my_array 10. Since the array indices are 0 to 9, this is an out-of-bounds access, leading to a kernel panic. Compiling and running asterisk. 1. Save asterisk. Save the code as my_kernel_module.c. 2. Makefile asterisk. Create a makefile in the same directory. 3. Compile asterisk. Run make in the directory containing the files. 4. Load asterisk. Load the module using sudo insmod my_kernel_module.ko. Observed error asterisk. You will likely see a kernel panic, and the console will display an error message similar to this. Debugging process asterisk. 1. Read the error message asterisk. The message bug, array_index integer parameter out of range for buggy_ function is the starting point. It tells us that the array_index parameter, which we can infer is index in buggy_ function, is out of range within the buggy_ function. 2. Analyze the call trace asterisk. The call trace shows the path to the error. The important entries here are: asterisk buggy underscore function, confirms that this is where the error originated. Asterisk my underscore module underscore init, indicates that buggy underscore function was called from the initialization function of our module. 3 code review asterisk examine the code of buggy underscore function. The code directly accesses my underscore array using the index without any bounds checking. This is the obvious vulnerability. 4 examine the call site asterisk look at where buggy underscore function is called in my underscore module underscore init. We are intentionally passing array underscore size as the index, which is one element beyond the end of the allocated array, indices 0 to array underscore size, 1. 5 solution asterisk add bounds checking within buggy underscore function. This adds a check to ensure the index is within the valid range. If the index is out of bounds, it prints an error message and returns an error code. Alternatively, you could use bug underscore on, 1, to trigger a panic if an invalid index is encountered, making the bug more visible during development. Preventative measures asterisk. Asterisk always perform bounds checking asterisk when working with arrays or other data structures. Always check that indices are within the valid range before accessing elements. Asterisk use safe array access functions asterisk consider using helper functions that automatically perform bounds checking. While these may incur a slight performance penalty, they can greatly improve code safety. Asterisk use static analysis tools asterisk static analysis tools can detect potential out-of-bounds access errors during compilation. Asterisk use memory sanitizers asterisk enable memory sanitizers, Kazan, Kameson, during development and testing to catch memory safety violations. Asterisk be wary of user input asterisk carefully validate and sanitize any data received from user space. Asterisk use defensive programming techniques asterisk write code that explicitly checks for error conditions and handles them gracefully. Asterisk regular code reviews asterisk have your code reviewed by other developers to catch potential errors. Asterisk fuzz testing asterisk use fuzz testing to automatically generate inputs that can expose vulnerabilities in your code. In conclusion asterisk. The bug, some bad value integer parameter out of range 4. Error is a serious indication of a problem in the Linux kernel. By understanding the causes, using systematic debugging techniques, and employing preventative measures, you can effectively identify and resolve these errors, ensuring the stability and reliability of your kernel code. Remember to carefully analyze the error message, call trace, and surrounding code, and don't hesitate to use debugging tools like GDB or memory sanitizers. The key is a methodical and thorough approach. Good luck.